afternoon. In my last lecture, I was talking about fluidized bed reactor and I was discussing some design concepts of a fluidized bed reactor. And I told you that there are two kind of models available. One is Davidson model, which is known as two phase model. So, we assume that there is a bubble phase and then there is an emulsion phase. So, the reaction takes place between bubble phase and emulsion phase, and there is some kind of transfer of mass from bubble to emulsion, that is a simplest model if you look at the actual hydrodynamics of a fluidized bed reactor. There is another model which is known as three phase model. So, in the three phase model, as I was discussing yesterday also, so bubbles are covered by solids. So, if you look at the fraction of the solids in bubble phase, so if I talk it FB, which is in terms of the volume of the solid in the bubble phase divided by the total volume of the bed, that is the fraction of the solid in the bubble phase. So, that is a very low number, say 0.001 or it may be 0.001 to 0.01, low number. So, there is a very low chances of reaction, because reaction needs a solid surface or catalyst surface. So, the chemical reaction will be low. So, this is one, and then at the lower side of the bubble, which I was talking last time also. So, this is a kind of the shape, if you look at a gas bubble which is moving. So, this is surrounded by a solid particle, and this is our cloud phase here. So, these are the particles, right, solid particles. So, this is the cloud of the solid, and this is your gas bubble, and in between lower portion you will have some more concentration of the solid here, and this is known as a wake phase, right. So, you have a cloud phase, you have a wake phase, and then far away from this you have a solid particles, and that is known as emulsion phase. So, in the emulsion phase you have more solid. So, here you will have more solid material, catalyst material, and less gas. Here you have more gas and less solid in the bubble phase, and we are talking a transfer, that is mass transfer and chemical reaction depending upon the type of the kinetics of the reaction. So, this is what has been shown here, that a fraction of the solid mass which is present in the bubble phase, and there is a volume V 1 of the bubble. So, when you have a superficial gas velocity u 0, and in model it is splitted like this. So, there is a kind of bubble phase, there is a emulsion phase, and there is a transfer mixing, right. So, that is known as cross flow coefficient, that is from bubble to emulsion when you have just a two phase model, right. So, and then at the exit these two merge, and we have some average conversion or CE, and here you have some inlet concentration C 0. So, basically it is a kind of a combination of a plug flow reactor and a with certain degree of mixing. So, you can see here the plug to mix flow. So, you will require a term like a dispersion number d upon UL, which is in the bubble phase, and same thing again here is a kind of the plug flow and the mixing, that is the CSTR. So, some kind of degree of back mixing. So, this is your d upon UL 2, that is the dispersion number in the emulsion phase. So, these are the volumetric flow rates, that is in terms of the bubble, volume of the bubble and volume of the emulsion. So, we are talking the concentration of the gas in bubble phase and concentration of gas in the emulsion phase, and then there is an average concentration of gas in the exit. So, how this the concentration of the reactant species change as it moves from this point to this point in a fluidized bed reactor. So, this is tell you the conversion or the productivity in a process. So, accordingly you need to size this reactor, that is the height of the fluidized bed reactor is to be decided. So, this is what you can see here, the actual condition. So, you have a emulsion phase which is shown by the dot of particles. This is the bubble which is just like this is your bubble phase, and there is a cross flow, that is the mass transfer, right. And this is what the I was talking here, that you have a three phase system now actually, right. So, the bubbles are, so what when we write a three phase model which is known as a Kunney-Levenspiel model, KL model. So, there is a bubble there is a cloud phase which is shown by this dot line like this. So, this is your cloud phase and this is your wake here at the lower portion of the bubble, right. And this is the fraction of the solid in emulsion. So, F E. So, that is the volume of the solid in emulsion phase per unit volume of the bed, right, or in terms of mass also, mass of the solid in emulsion divided by the mass of the bed. Same thing, this is the cloud phase. So, mass of the solid in cloud phase divided by the mass of the bed, and this is the bubble phase. So, definitely the concentration of solid in the bubble phase will be very low. So, chemical reaction in the bubble phase is low, right. So, the reaction is in bubble phase, reaction is in the cloud and wake phase, and reaction is in the emulsion phase, but the degree of contribution is different. So, this is what the very complex series parallel resistance because of all this mass transfer and chemical reaction. So, as I said that the gas is entering like this. So, this is your entrant point and then this is your exit point. So, during this when you look at a model, a 3 phase model. So, we have something like this, right. So, you have a reactant A which is in the bubble. So, concentration of the reactant in the bubble, right, or transport or mass of the reactant in the bubble. So, partly it transfers to the cloud phase and partly it reacts here. So, so total mass balance if you look at, so moles of A, right, or reactant A which is transferring to partly to the cloud phase and rest is reacted there. So, since the concentration of the solid here is low, so this reaction will be low. So, this is what is here what discussed in this, that there is a transfer. So, this is the cross flow transfer, right, the bubble to emulsion which is in the 2 phase, and same thing here in between because there are solids present, fraction of the solids present. So, there will be a reaction, catalytic reaction. So, partly it is reacted and partly it is transferred. So, this is equal to this plus this basically, right, and when it reaches into the cloud phase, then again there is a reaction in the cloud depending upon the concentration of the catalyst present. So, there is a reaction in the cloud and the rest is transferred into the emulsion phase, and again when it reaches to the emulsion phase. So, because there is no zone for further mass transfer, so it is reacting in the emulsion and finally, it will leave the bed. So, just very briefly I will talk about the design concept because that is a design of fluidized bed reactor which is a separate course where you understand the hydrodynamics, calculate all these parameters, hydrodynamic parameter, calculate the RTD model, right, using to calculate the dispersion number and then correlate right for the exit H conversion. So, here in this I am very briefly talking about that when you use a catalyst in the fluidized bed reactor, what are the parameters required to design a fluidized bed reactor or what is the basic approach to design a fluidized bed reactor. So, I have just defined certain parameter here. So, U0 is the superficial gas velocity in the bed, that is depending upon the volumetric flow rate divided by the area of the cross section. So, based on empty bed. So, that is known to you. So, this is nothing but in terms of meter cube of gas per unit area of the bed per unit time. So, basically flow rate which is volumetric flow rate divided by the area of cross section which is pi d square by 4, where d is the diameter of the bed, right. Epsilon we are defining the void fractions in the bed, right. So, that is the fraction of the solid if you know in the bed. So, 1 minus that solid fraction is your total void fraction, right, in the bed. So, basically it is a bed porosity, and we represent these subscripts like B representing a bubble phase, C is representing the cloud phase, E is representing the emulsion form phase and W is representing a wake phase. So, generally the cloud and wake phase are combined together which is in the model, right, and so these define the different phase in terms of subscript. M and MF they are referring basically the minimum fluidized bed condition, right. When I write a B, it is a bubbling fluidized bed reactor and condition, right, and F is just basically the F is representing the bubbling fluidized bed condition, and this MF is representing a minimum fluidized bed condition, and when it is M, it is just representing a packed bed. So, when there is no velocity of the gas or very low velocity of the gas, so bed is stagnant, right, solid particle, there is no bubbling. But when you increase the velocity, now bed starts bubbling. So, there will be more and more void in the bed. So, that is what these are the different terms used, and when you increase the velocity to a extreme high, so that becomes a bubbling fluidized bed, and if you are even high, it will reach to turbulent conditions or fast fluidized bed conditions, right. So, we are not talking that part here. So, this is what the subscript written. So, when it is written KCE, so basically it is representing a cross flow coefficient or transport coefficient, which is representing CE. So, cloud and emulsion, right, between cloud and emulsion. Same thing here, this E is representing an emulsion phase, this C is representing a cloud phase. FE, I told you, it is the fraction of the solid in emulsion phase, FC fraction of the solid in cloud phase, FB fraction of the solid in bubble phase, and W is representing a wake phase. So, in order to understand the transport property, as I said that there is a reaction and there is a mass transfer. So, this is what here you have a gas at superficial velocity u0. So, this is representing the superficial velocity of the gas, right, and passes through the bubble, right. So, total volumetric flow rate is constant. So, u0 is again the superficial gas velocity in the exit. So, there is a transport, but the 3-phase model we have said now. So, that has been shown now. There is a bubble, there is a cloud and wake which is combined now CW, and then there is a other phase which is where you have more solids. So, that is known as emulsion phase. So, rest of the emulsion. So, there is a transfer from cloud to emulsion, right. So, this is what shown here, transfer from bubble to cloud. So, that is shown here, right, and this is the actual picture in a bed. So, you have a superficial gas velocity u0. So, this is superficial gas velocity, right, meter per second. This is the what the bubble is moving up. So, this is basically a bubble velocity which can be calculated from the mass balance, right, and this is what the for gas which is either up or down, because there is a movement of the solid particles or circulation here, right. So, it is moving up and down. So, this is your emulsion phase, this is your cloud here in the bubble, this is wake here, this is the bubble here. This, so all this terminology has been discussed. So, this is basically a Courtney-Levenspiel bubbling gas fluidized bed model, right. So, what happens? Whatever the we have seen, the mass transfer is taking place, chemical reaction is taking place. So, that steps during a 3-phase model or steps which have been discussed here in this, the same thing have been defined here. So, first step is your mass transfer from the bubble to cloud wake phase, that is the mass transfer, right. So, one can calculate from the mass transfer coefficient and the concentration difference in the 2 phase, that is concentration of gas in cloud and in the wake phase, right. So, bubble, that concentration of gas in bubble phase and concentration of gas in cloud and wake phase. So, that is first thing, a mass transfer. So, there is a possible chemical reaction in the bubble phase also. So, that is the we have said that there is a chemical reaction, but since concentration of the catalyst in this phase is low. So, this amount of reaction will be negligible, right, because amount of catalyst in the bubble phase is low. So, the reaction possibility or the rate of reaction or the moles transport because of chemical reaction will be low, right. So, ultimately the transfer is because of mass transfer, right, and because of chemical reaction. So, this is the first step. Second step, when it reaches to the cloud and wake, right. So, mass transfer of reactant into cloud and wake, which is CW phase from bubble phase, right, and from there into the emulsion phase. So, again now there is a cloud and wake. So, there is enough concentration of the catalyst. So, there will be a chemical reaction also in the cloud phase. So, this is your this step here, right. So, first is this one, which is transfer from this to cloud and wake now, which is combined cloud wake, and from there it is transferring into emulsion. So, this is transfer into the emulsion, and also there is a chemical reaction because it has the catalyst there. Here also there is a reaction, but this contribution will be low because the catalyst concentration is low in this zone. So, this is your second step, where the transfer from cloud wake to the emulsion phase right, and there is a chemical reaction. And then third step, when it reaches to the cloud and wake, there is no mass transfer, mainly it is a chemical reaction. So, that is basically in the emulsion phase, right. So, mass transfer of reactant from cloud wake phase to the emulsion phase, that we already talked, and now there is a chemical reaction in the emulsion phase, and there is no further transfer, right. So, all these steps can be written mathematically in terms of material balance, which has been discussed and should be clear now, that whatever the disappearance in the bubble phase. So, whatever the gas which is present in the bubble phase, that has gone to the cloud and wake phase, and that has partly reacted. So, it means the transfer, that is the loss in the bubble phase, right, for gas is equal to reaction in the bubble phase plus transfer to the cloud wake phase, right. So, that is the material which has been disappeared from the bubble phase, that has partly reacted, chemically transformed into the product, and partly it is transferred to the cloud and wake phase. So, that is the first one, which is step, right. Second one, the whatever the material which is transferred or lost from the cloud wake now, or what is material which has come to this transfer cloud wake phase, that is partly reacted and transformed into the product, and whatever which could not react is transferred into the emulsion phase. So, again there is a mass balance here. And the third one, in the emulsion phase, whatever the material which is transferred to the emulsion, that is equal to the reaction in the emulsion phase, right. So, that is a chemical reaction in the emulsion. If we define this FB, which is the volume fraction of the solid in the bed, we have already defined. FC, F subscripted HC is the volume fraction of the solid in the cloud phase, and Fe is the volume fraction of the solid in the emulsion phase, right. So, these are the terms which we have defined earlier, that is the volume of solid in the bubble divided by the volume of the bed. So, that is your FB. So, you can very easily write down the rate of disappearance of B, which you write minus dCB by dt, that is change in concentration of B with respect to time, rate, right. So, and you know now that Fa naught dXA is equal to minus Ra, right, and that is here mentioned in terms of this, right, convective term, which is FAZ, right, which is lost and between Fa at y, right, which is written in terms of Ca into U times A, right. So, basically it is a mole balance. If I write Fa, which is the at y, same thing at y plus delta y, right, something like this, and this is happening in a column where this is your y and this is your y plus delta y. So, basically this y is the height of the column, right. So, we can find out, to achieve a given conversion, what should be the height of the column, if you know how the concentration change between two sections, right, between y and y plus delta y, right, and this is what we are writing a material balance simply. So, Fa is what? Concentration into volumetric flow rate, right, or volumetric flow rate is area of cross section multiplied by velocity. So, this is what written here, and when you write a differential, then this thing we have already done. So, minus UB, that is the bubble velocity, UB is the bubble velocity, and dCB by dy, that is now the change in concentration with respect to y, right. So, this is equal to, now this is transport basically dFA by dy, right, change in moles of A, right, per unit depth, right. So, that is the reaction, that is this is a chemical reaction in the bubble phase, right, and that will depend on the concentration of the solid which is present in the bubble phase. So, that is why FB, because we are writing per unit mass of the catalyst there, and we have reported it, FB is a fraction of the solid or volume fraction of the solid in the bubble phase, although it is a low number 0.01 or 0.001 as I said, right. So, times the chemical reaction rate constant times the concentration. So, minus Ra is equal to Kca, something like that, right. So, we are assuming a first order. So, that is written a chemical reaction term here, plus there is a transfer, mass transfer, which is from bubble to cloud and wake phase. So, this is your overall cross flow coefficient, this is a kind of cross flow coefficient, right, between bubble and cloud. So, one can determine it experimentally or based on the hydrodynamic study, because it will depend on the diameter of the bubble, velocity, so many other parameters, right. So, KBC and times concentration of gas A in bubble phase minus concentration of gas A in cloud phase. So, this is your mass transfer to cloud. So, the first step which I said is that the transfer or disappearance in the bubble phase is equal to transfer to the cloud and wake phase plus the chemical reaction which is here. So, chemical reaction plus mass transfer, and now this whatever you got in this cloud phase, this one KBC Cb minus Cb, because this is the material which is available in cloud and wake phase, and that is again partly reacted. So, will depend on the concentration of solid in cloud wake phase times the chemical reaction rate constant times the concentration of gas A in the cloud phase, right, plus there is a transfer also, that is so mass transfer. So, again this is a cross flow coefficient KCE in cloud to emulsion times the concentration different. So, this is a mass transfer rate, Cc concentration of gas in the cloud phase minus concentration of gas in emulsion phase. So, this is your second step what we discussed in the earlier slide, right. Now, this thing is reached into the emulsion phase and that will react chemically, which is here. So, this is KCE Cc minus Ce, which is the material available in the emulsion phase, is reacting chemically, which is the mass fraction of the solid in the emulsion phase times again the kinetic and times the concentration which is available in the emulsion phase, right. So, this is what the simple material balance, right, for this kind of situation, right. So, now you can eliminate them easily, you can add them, or these all can be eliminated, and you have the concentration expression in terms of bubble phase concentration, right. So, you have now just simplify it. So, you have minus ub dCb by dy which is here is equal to some overall constant, because you will have this cancels, this cancels. So, remaining terms are in terms of this kinetics, right, this and this term, right. So, overall some constant which we call Kf, right, overall rate constant, which will have some contributions of the resistance. So, Kf times Cb. So, now this is a function of Cb. So, one can integrate this equation easily and find out how the concentration change down the or to in a fluidized bed reactor. So, this Kf is represented something like Fb times Kr plus 1 by beta, which is nothing but the constants obtained from this. So, Fb times Kr plus 1 by beta. So, Fb times Kr you have already seen here, and these are the rest of the terms mentioned here. So, beta is defined by 1 by KBC plus 1 by Fc Kr plus 1 by alpha. So, again alpha is 1 by KCE plus 1 by F Kr. So, thus you do the exercise here, how did you get it? So, you can do it because it is not difficult, just you have to add all these terms, right, and eliminate it, eliminate the intermediates. So, you can find out the overall rate in terms of the bulk Cb bubble concentration, right, and the other terms are nothing but the contribution of chemical reaction resistance and the mass transfer resistance, that is the cross flow coefficients what we are talking. So, this is what the different terms defined. So, KBC which is the cross flow coefficient from bubble to cloud, and this is the kinetic term, again this is the mass transfer coefficient basically, or cross flow coefficient in the emulsion side, cloud to emulsion. So, this is representing a kind of resistance offered in the cloud emulsion phase, right, and this is representing a kinetic resistance. So, it is basically the number of resistances which are present during the fluidized bed reactor, and you have to minimize those resistances. So, you have to do the hydrodynamics, you have to look at the effect of particle size, gas velocity, and then try to design the fluidized bed reactor, right. So, if you integrate this expression from C0 to Cb, inlet is C0. So, you have Cb divided by C0 is equal to exponent of minus Kfy divided by ub. So, this is this expression, you have this expression here. So, just integrate dCb divided by Cb is equal to your Kf divided by ub minus, right, and dy. So, integrate it when y is equal to 0, your concentration is C0 and at any value of y concentration reach to Cb. So, integration of this, right, which is ln of Cb, and that can be substituted now in terms of limits. So, Cb by C0 is equal to exponent of minus Kf y upon Ub, right. So, this is how do you find out that, suppose if I now have a Cb value which can be written in terms of C0 1 minus x bar basically, because you can have different residence time for each size particle. So, some mean conversion of the solid. Same thing is Cb is also for a given size of particles, right, mean conversion or mean concentration in the bubble phase. So, one can find out this value or conversion value, and one can correlate that with the height of the fluidized bed reactor. So, y, right, and this is how we proceed for the design. So, one can find out the overall conversion, as I said Ca is equal to Ca naught 1 minus x. So, 1 minus x is equal to exponent of minus Kf L upon Ub. So, y is now defined by L, where L is the height of the fluidized bed, right, and there is always a material balance. So, either you write in terms of height, initial height into 1 minus epsilon m, that is the epsilon m is the packed bed void fraction, right. So, this is representing L 0 into 1 minus epsilon m is represent, because 1 minus epsilon m is representing the fraction of the solid in the bed, right. So, L 0 into 1 minus epsilon m is representing mass of the solid, and that any height it will remain same, mass will not change, catalyst mass, right. So, that is in the fluidized bed times the bed fraction of void fraction when it is fluidized. So, 1 minus epsilon f is again the solid fraction, right. So, this is simply material balance which can correlate your initial height of the bed and height when the bed is fluidized, right. So, and epsilon f is the porosity of the fluidized bed. So, one can very easily write, because epsilon f is the 1 minus epsilon f means solid fraction, and that will be related to the bubble, solid in bubbles plus solid in clouds plus solid in emulsion, right. So, fraction of the solids which is present in the bed and multiplied by the delta. So, delta is the volume fraction of the bed which is taken by the bubbles, right. So, that is the volume of bubble divided by the volume of the bed, that is your delta, right. So, this is what the expression, your Fb plus Fc plus Fe is total fraction of the solid which is representing from, or which can be correlated with the 1 minus epsilon f. This is the solid fraction, because epsilon f is the void fraction in the fluidized bed, and same thing in terms of the height of a bubbling fluidized bed, which is written in terms of mass of the catalyst divided by density of the solid, this is density, right, times A times 1 minus epsilon. So, simple mass balance basically, right. You have done this, that how to calculate the height of a bubbled fluidized bed, right, which will relate to the mass of the catalyst in the bed divided by the density of the solid. So, this is basically the volume of the catalyst in the bed, right, and you know volume divided by area of cross section, that will be equal to height, right, and since this height is related to the fraction of the solid fraction, right. So, 1 minus epsilon f representing the fraction of the solid. So, because actual height is low, but since now solid is covered in between in the interstitial space of the solid, you have a gas. So, what will happen? The height will increase, right. So, the total height, if you have a packed bed reactor, the height will be lower. So, if you have a fluidized bed reactor, the height will be increased, right, by what fraction, that will depend what is the volume of the gas in that section, right, and this is the volume of the gas which we are representing in this form, right. So, either you write a solid balance or you write it in terms of the volume of the gas which is in the bed, right, between the particles, something like the gas which is in the pockets between the particles, right. So, that volume plus the volume of the bed, that is catalyst volume, that is the total volume, right, related with the height. So, all these parameters like your minimum fluidized bed velocity which you do from the experiment, right, minimum bed porosity epsilon f, superficial gas velocity required, alpha which we are defined in terms of the resistance, right, and effective bubble size dB in the bed, right. So, these are known basically in the model, right, a property, right, and once you know this, then you can very easily define the hydrodynamics, right, bed flow, flow regime, interchange rate, that is mass transfer rate, right, and then finally, you can correlate it with the height of the bubbling fluidized bed, right. So, that is a fluidized bed reactor design. So, but there are lot of further complications when you look at the hydrodynamics. You have to study RTD to get the mean conversion. For different size particles, you have to find out their average length of stay, right, and then there may be illustration, some of the particles may leave the bed. So, all these complications will be there when you look at a fluidized bed reactor design, right. So, but once you have a efficient design for better heat control, when the reaction is highly exothermic, right, it is a good type of reactor system, because it has the combination of a mixed flow and a plug flow, right. So, I am not going in detail of rest of the things, because this is simply a material balance, right, and one can write the buoyant force, viscous force, react force, all these which are read in your particle mechanics or fluid mechanics. So, one can, what I mean to say, that your bubble rise velocity is a function of the diameter of the bubble, right. So, one can correlate it, can find out the at what velocity the bubble is rising, and the bubble velocity is related to your u0, right. So, u0 minus umf is basically the effective velocity which is required for fluidization, because up to umf it is a packed bed, right. So, you have to give above umf if you want to make it a bubble bed, right, and then bubbles are rising in the bed. So, actual the bubble velocity is related to the u0 minus uf plus some bubble rise velocity, right. Delta, I told you, it is the bed fraction in bubbles. So, volume of the bubbles in bed, that is gas volume, right, gas bubbles divided by the volume of the bed, delta. And delta is related to, now because what is delta? It is related to the volume of the gas which is in the interstitial spaces, right. So, when it is a UMF, the particles are close together, packed together. When you have put the gas above UMF, now particles are moving up, right, bubbling in the bed, and in between you have pockets of the gas. So, that can be correlated with this U0 and UMF. So, delta is effectively 0 when it is a packed bed, right, no gas in that, right, and this is U0 minus UMF divided by UB, bubble velocity. So, one can find out all these parameters and then design a fluidized bed reactor. So, this is about the reactors which we are talking in the say multi-phase reactor. So, we were talking about a trickle bed reactor, very effective reactor in the petroleum refinery, right. Same thing, the fluidized bed reactor, very important when you have the fluid catalytic cracking, and then design easy in order to say that you can regenerate the catalyst, right. Although design is not very simple, but reactor and regeneration combination is possible in these kind of reactor. Then there are slurry bubble column reactor, right, suspension reactor. So, different kind of reactor system can be used for a given catalytic system. So, one has to identify a process, one has to look at the hydrodynamics, one has to look at the experimental conditions required in order to achieve the high conversion and high productivity, and then need to select a design, good design or good kind of reactor, and then design of that reactor, right. So, again very quickly I will just go to some of the process which are very widely used or very important, refinery process or petrochemical process, right, and say hydrogen production, which is very important in the fertilizer as well as in the refinery, because the hydrogen consumption, huge amount of hydrogen is consumed in the refinery as well as in the fertilizer. Fertilizer industry generally for the urea production they use the large amount of hydrogen, and similarly in the case of petroleum refinery, hydrocracking, hydrodesulfurization, right, hydroisomerization. So, a large amount of hydrogen is required, and so hydrogen production becomes a very important issue nowadays, that how to enhance and to get it from the renewable sources, right. That is very important with respect to the current scenario. So, lot of catalysts are being developed, or lot of the processes are being developed in order to just develop or efficient hydrogen production method. So, this is one steam reforming process. So, all of you know that steam reforming, generally naphtha reforming, naphtha type of reformers are used for hydrogen production, right. And nowadays natural gas is available in plenty. So, a bi-fuel type or naphtha reformer and the natural gas based fertilizer plants are also available, right. So, gas plus naphtha in order to balance the amount of carbon dioxide that is also being practiced. So, generally reforming, all of you know, you have a methane natural gas reforming. So, this is a natural gas, basically I am saying here methane plus water, and it gives you carbon dioxide CO2, right, and plus hydrogen, right. So, basically the other option is syngas also, where you have the partial reforming and partial oxidation also sometimes. So, that gives you the syngas also, that can be used for liquid fuel production or alcohol production, and widely being practiced. Fischer-Tropsch type of reaction is used there also, right. So, the any hydrocarbon again here that not only this methane natural gas. So, what I said naphtha is also being used, right. So, CNHM, which may be any combination of paraffin, naphthenes and aromatic. So, and reacts with some water molecules and gives you carbon monoxide and hydrogen, right. So, this is a kind of syngas production, and which can be reformed further. This syngas can be converted again by water gas shift reaction, which is shown here. So, you have a carbon monoxide and water, and reacts you get carbon dioxide and hydrogen, right. So, the contribution is something like this. If you look at here, this reaction is highly and this reaction is yes endothermic reaction, right. And here if you look at, this is an exothermic kind of reaction. So, reforming requires a lot of amount of heat or during this process, right. So, endothermic reaction, exothermic, or if you have something like a partial oxidation, if you add little bit oxygen, then it can be a kind of autothermal type of reaction also, right. So, this is what the trend in the refinery, fertilizer and also in petrochemical industry for hydrogen production, right. So, the typical composition of natural gas, because it is available in plenty nowadays and transported through the pipeline. So, this has become one of the reasonably good source of hydrogen production, right. So, roughly it contains more than 90% of methane, which is mainly methane, right, but besides methane. So, it can be the wet gas, something like that. So, it may have the heavier fractions like ethylene, propylene, some C4 plus, right. So, these are known as the heavier fractions or natural gas liquids, right. So, they may also be present, and then there may be some carbon dioxide and sulfur. This is the problem in fact in natural gas, when you have to remove the sulfur before treatment in order to avoid the deactivation of the catalyst. So, now reforming, the most common catalyst used in the reforming is nickel based catalyst, right. So, this is one of the most common catalyst, because it is economical, right, and available also, but this palladium, platinum, ruthenium, rhodium, iridium, they can also be used, and they may be more effective. In fact, even a low concentration of these material may be good for catalytic activity, and that is what being looked nowadays in order to have the highly efficient reactor, or if you want to look at a small size reactor, you need a more active catalyst, right, where the size of the reactor can be reduced, and a kind of micro reformer, that is the concept, where we need a from large scale unit we want to go in a small or channel type reactor, right. So, that is one R&D area where the one needs to look at the new kind of reactor design, new kind of novel catalyst, where the system can be smaller and smaller. So, iron and cobalt have also been tested, right. They are also very active, but they can oxidize easily because lot of water is present. So, that may not be good for the reforming reaction. There are a lot of challenge in the steam reforming. So, process is available in terms of the reforming as far as the technology is known, but as I said that nowadays the trend is different in terms of the E factor, atom efficiency, and highly efficient catalyst and novel reactor design, right. So, new kind of reactor design is required, or new kind of reactors are to be fabricated or designed in order to produce the efficient hydrogen with low carbon dioxide or carbon monoxide, if you have just the hydrogen production, right. So, the reforming catalyst is very robust, right, but lot of carbon deposits on the catalyst. So, the deactivation of catalyst is an issue. So, life of the catalyst may be just 1 year or maybe up to 3 years. So, catalyst like say Handler, Topsoe, Snam-Pragati, lot of licenses are available UOP, right. They have provided the catalyst and the reactor design for this reforming reaction, but still one needs to look at the novel approach or new kind of catalyst, right, in order to reduce the deactivation of the catalyst, because every 3 years the catalyst is to be replaced after every 3 years. So, it means the solid material which is now as a waste now the catalyst, right, that is to be dumped somewhere. So, disposal of these kind of solid waste is again an issue. So, it is a problem, right. So, we need to find out a different catalyst, either more active catalyst or look at the how to reuse the catalyst into the process. So, So, this is again an issue or where the R&D is required, right. So, several reactions like this secondary reaction which happen, they may tend to form carbon. So, lot of secondary reaction also takes place during this. So, it accumulates on the surface of the catalyst. So, life of the catalyst decrease, right. So, how to reduce the carbon formation? So, that is again important to give a thought. Then so, it depends like the probability of carbon formation, this increase, right, with decreasing oxidation potential. So, if you have a lower oxygen steam or oxygen content, right. So, your carbon formation may be more and more, right. So, but again the larger amount of steam is generally used because lower amount of steam should be used theoretically, but otherwise you are increasing the loading on the reactor. So, higher the steam, your coke formation will be low, right, but how much, that is important. So, one needs to check the optimum concentration or steam to hydrocarbon ratio for the process, right, but very high amount of steam cannot be used because it unnecessarily dilutes the reactor and the reactor sizing will increase, right. So, one needs to check that. So, new trends are looked into. So, one thing is that thermodynamics, right. So, you know that when the methane produces, right, or methane reforms or any alcohol reforms or partially oxidized. So, we get hydrogen, carbon monoxide, carbon dioxide, right, and maybe the some other unwanted product also. So, there is some kind of equilibrium conversion during the process. So, if somehow this CO removal system like say for the fuel cell application where the hydrogen is required, right, pure hydrogen is required because the electrodes which are generally used in the fuel cell, they have the platinum or palladium type electrodes. So, small concentration of this carbon monoxide may poison the catalyst, right. So, it means this something is to be done. So, in order to increase the conversion, increase the productivity and also increase the life of the catalyst. So, new concept may be something like this here. So, instead of a packed bed reactor, so presently this reforming is done in a large number of tubes, right, they are placed there, right, or a just single reactor. So, it is very difficult to dissipate the heat, right, or you need a good kind of heat exchanger, that is a problem. Simultaneously deactivation of catalyst is the problem. But if you have something like this where you have suppose a methanol reformer or methanol partial oxidation, so you are generating the hydrogen, right. So, if you have a porous membrane, right, a ceramic type membrane porous material, so hydrogen will diffuse into this, right, like this, but larger molecule cannot diffuse like CO2 they will remain here, right, one can recycle it also. So, now you get pure hydrogen here, right, you purge this gas and take this hydrogen into a fuel cell unit and you can have the pure hydrogen required for the fuel cell, and here you are disturbed the equilibrium. So, more and more conversion will take place. So, these kind of reactors are nowadays being considered, or what in this is a kind just an example of methanol reformer, right. So, catalytic membrane reactor. So, membrane type of reactors can be the one of the option in the future for the hydrogen production, right, for fuel cell application especially. And then these are the kind of ceramic monoliths, a channel type reactor, right. So, where the in this reforming reaction say effectiveness factor I told the diffusion length, right. So, that is your which is related to the size of the particles and the resistance non porous materials, right, or microporous material. So, your effectiveness factor is very low 0.01, 0.001. So, it means your actual rate is very low, right. When rate is very low, your conversion will be very low, or you need a large size reactor, right. So, reformer is the one kind where you have a height 10 to 15 meter, something like that, right. So, if you need a smaller units, so you have to look at those things, that prepare the catalyst in such a way like wash coating of this, right, where the diffusion length is very small, right. So, your resistance for diffusion will be reduced, and this is what a kind of monolith here which is shown in the process, right. It is a kind of channel type reactor, right, and this is what the actual, if you look at here the model where you have the small, right, these are channels here in this area. So, and this is known as the cells per square inch. So, it can be 200, it can be 100. So, this is just like a grid here. If you look at this top section, so it will look like this, just like the your sieve, right, like this. So, you have the square openings like this. So, number of just like in a mesh you define. So, number of cells per square inch, CPSI we call it, right, cells per square inch. So, this may be 200, this may be 400. If it is 400 means it is still a narrower channel, and these are known as micro channels, right. And in between we can wash coat our catalyst. So, now the diffusion length is very small, and each channel is acting because it has now large surface area per unit volume, right. So, this structure. So, it has the channels, it has the openings, right, with different size. So, it will have large surface area per unit volume. So, this is known as a chordrite structure, monolith, right, a type of structure, right, and this is what here it is shown, a ceramic monolith where you can see the larger openings here. So, through this the reaction or the reactant species pass, they diffuse also, right, axially and radially, right, and then they transfer into the reactor. So, large surface area per unit volume. So, for your automotive exhaust catalyst also this kind of structure is used, right. So, at the exhaust we put this kind of material which is coated with the platinum or noble metal, right. So, and then it gets all these NOx, SOx, COX. So, three-way type of catalyst, there reduction, oxidation, all these type of monoliths catalysts are available, right, and these are now being considered for the reforming. The same thing is that just like in a plate and frame heat exchanger. So, this is a kind of the system, right. So, you have the something where the fluid goes and path follows a zigzag path like this. So, this is a channel like this, right, it will go like this. So, again you have a large surface area per unit volume, and just like in a plate and frame. So, something goes from this side and then comes down like this, right, flows on these channels, small channels, right, of 0.1 micron. So, small depth channels they are available, and this is known as a micro reactor, and nowadays widely being considered for the reaction like reforming, right. So, these are some, again this is a honeycomb type of structure, right, metal honeycomb. So, again a corrugated path is being used here. So, these are some new concepts which are generally considered, right, especially when the large surface area per unit volume is desired. Again you need to, when you look at a new kind of design, you need to look at the transport properties in that, right. So, here again you will have different kind of transport properties, you need to look at the mass transfer, right, you need to look at the heat transfer, convective mass transfer, diffusion transfer. So, very quickly just because I am not going to talk on the design of this kind of reactor, but the step if you look at in terms of transport properties. So, you have a convective flow, right, of reactant, right, because of the velocity terms, right, C into V what we are talking. So, convective flow of reactants and products in the direction of flow through the channel, right. This is the convective. Then second is the diffusion and dispersion of component in axial and radial direction, right. So, similar steps what you have seen there in a pellet also, the approach is similar, right. There it is a pore, now we have a channels here in this, right. Then momentum changes because of the pressure variation, right, this is also very important here, you need to check that, right, transport viscosity and all these behavior, right, pressure drop, convective heat transfer in the direction of flow. So, all these things are required to look at, right. Then conduction of heat, right, because it is a metallic monolith. So, there will be heat transfer through the conduction also. Then radiation, because high temperature. So, there may be a radiation also, right. Then there is a chemical reaction also because it is a monolith wall, right, on that you have a catalyst. So, there will be a catalytic reaction, and there are channels. So, there are lot of pores just like pore space of a catalyst, void space, and in the void space you do not have any catalyst. So, there will be the thermal reaction also, so homogeneous reaction, right. So, you have to look at all these steps when you look at a new kind of monolith design or a kind of honeycomb reactor design, right. So, these needs to be checked. Similarly, so the reactors which are generally used in the refinery petrochemical, right. So, they are plug flow or mixed flow. So, I already talked on that, right, a bubble column reactor, slurry bubble column reactor. So, these kind of reactors which may be a combination of a plug flow reactor or a CSTR type reactor, right. So, contacting patterns should be known, that is very important, we have discussed, right. And suppose the catalyst is very expensive. So, heat transfer or removal of heat is important, otherwise the catalyst life will damage. So, you prefer a fluidized bed reactor because they are, it is easy to dissipate heat, right. Then mass transfer is again an issue. So, for high mass transfer you prefer a plug flow reactor, right, that high velocity at high superficial. So, all these kind of reactors are used in the refinery and petrochemical reaction, right. The important reaction if you look at the refinery and petrochemical. So, there are alkylation, isomerization, cracking, hydrocracking, dewaxing. So, all these kind of reactions are taking place in refinery, and the petrochemical reaction also you have the polymerization reaction for the manufacturing the high density polyethylene, low density polyethylene, and different kind of say polypropylene, and then styrene, butadiene, rubber. So, lot of if you look at the refinery petrochemical fertilizer, a large amount of catalysts are being practiced, right, and the type of reactor design will depend on the kinetics, it will depend on the hydrodynamics, heat transfer, exothermicity of the or endothermicity of the reaction. So, very quickly just the alkylation, say if you look at a very important reaction, right, where you are adding an alkyl group to a molecule, right, and this is generally catalyzed by either acid catalyst or basic catalyst. So, when you have acid catalyst, so they mainly do the aromatic alkylation in the ring. So, ring is alkylate, right, and when you have basic catalyst, then it just prefer the side chain of that reaction, right. So, if you look at that just alkylation, so you have just say a component like this is your toluene, so a ring compound, and you can have any compound here, ethyl benzene also, right. So, it reacts with the methanol. So, you have if acid catalyst, so it makes a para-xylene here, right, and if you have a basic catalyst, it makes the ethyl benzene. So, you can see that depending upon the catalyst type of catalyst, their concentration of the active site, your product distribution changes, right. So, this is a kind of alkylation reaction. So, depending upon the acid catalyst or basic catalyst, your product distribution will be different. So, the most of the catalysts which are acid catalyst used in the case of alkylation. So, alkylated gasoline is very important product in the refinery, right. So, alkylated gasoline which has higher octane number, right. So, this is generally HF alkylation I was discussing earlier. So, hydrofluoric acid is used, which is very strong acid. So, nowadays trend is that how to replace this hydrofluoric acid or sulfuric acid, because for polymer gasoline again, right, isobutene, that is one alkene and alkane can react and you can higher say isooctane type, right. So, this is again sulfuric acid is used as a catalyst. So, all these are highly acidic. So, a different kind of material of construction is desired. So, new trend is that use the catalyst something like a solid catalyst, right. So, although not well documented or not very popularly commercialized, but new trend is that one needs to look at the solid catalyst for the process, because they are easy to handle and material of construction is not an issue for them, right. So, these are the catalysts which are being used, right. So, typically the alkylating agent, the reactants are olefins, alcohols, ethers, alkyl halides, dialkyl carbonates, all these are used for the alkylation. So, as I said that it is a very important reaction in the industry. So, benzene and ethylene, the product is ethyl benzene alkylation, J2SO 5 is used as a catalyst and process is something like a commercial process here, right. Toluene and methanol, it gives you para-xylene. So, again J2SO 5 type catalysts are used here. Benzene and propylene reacts, isopropyl benzene is the product, cumene, solid phosphoric acid and zeolites are used as a catalyst. Same thing here, benzene plus C10 to C13 olefins, we get linear alkyl benzene used for making the detergent, right, and here again the proprietary catalyst. So, lot of R&D is again being done here in these areas to develop new catalysts and new process for the reactor commercialization of the process. So, this is just a different kind of isobutane, isobutane, these react generally for making the isooctane, right, which is alkylated gasoline or something a polymerization polymer gasoline. So, these are the catalysts generally used in the refinery also to make the isooctane or larger molecular weight compounds which can be added to the gasoline, right. So, these have higher octane number. Similarly, isomerization is also very important process. So, hydroisomerization, isomerization. So, isoparaffins are made in this, right, normal paraffin, suppose they are converted to isoparaffin because it has high octane number, right. So, this is again an important process in the refinery, right. So, wax isomerization for lube also this is done, right, because the pour point if that is the if it is a cold country, the material if it is wax it gets solidified, right. So, it will be very difficult to flow. So, flowability will be low, flow index is low. So, one needs to convert these wax materials, right. So, isomerization is done, which has now the in order to reduce the pour point, right. So, that is important here. So, light naphtha isomerization to improve the octane number, right. In petrochemical the para-xylene is important. So, isomerization is done to get more and more paraxylene. So, again here the catalysts are platinum, which is a metal part, right, on SAPO, which is a kind of silica alumina phosphate, what I was talking during the zeolite type catalyst, right, and same thing platinum mordanite catalyst, acidic alumina catalyst, these are used in these reactions. Platinum Jettison 5 catalyst on mordanite silica. So, all these catalysts are used for the process. So, these are some reactions which are generally shown in the isomerization, and one can look at, and depending upon the catalyst which is used, one can have the process, and that is in terms of the concentration of ortho, meta, paraxylene. So, these are a kind of selective. So, shape selective zeolite materials are preferred here. So, same thing for isomerization of alkanes, right. So, we need to look at a higher octane. So, in order to produce more and more high octane gasoline. So, here platinum based, which is a bifunctional type catalyst now. So, platinum improves the hydrogenation activity and dehydrogenation activity. Second is the acid function, which is from the support side, right. So, it promotes the cracking activity like this, right, hydrocracking activity. So, alumina, silica, alumina, zeolite, they are used. So, it is a bifunctional which has the acid and metal catalyzed. So, you can see here some reactions are promoted on acid sides and some reactions are promoted on the metal side here, right. So, depending upon the requirement, a combination of the two catalysts can be taken in this. Similarly, cracking reaction, and where again the larger molecular weight compounds are cracked into smaller, and again zeolite or silica alumina type catalysts are used in this process. Propylene is nowadays in the refinement petrochemical, the high yield of propylene is desired. So, how to improve the propylene yield, right. So, selective catalysts are required, which can produce which can maximize the olefins, especially the propylene, right, and that is generally for the petrochemical purpose, right. So, when you have a pyrolysis type process where the hydrocarbon is cracked and you get more and more olefins in that, right. When you have a refinery process, you do the cracking, but intention is to get the gasoline range of hydrocarbon. So, for cracking purpose we use generally in the refinery a zeolite based material, right, just what I said FCC gasoline. But in the case of pyrolysis process, which is for the petrochemical industry, we take something like silica alumina type catalyst, right, a different kind of catalyst system, calcium aluminate type catalyst, magnesium aluminate. So, they enhance this olefin production, right. So, that is again a challenge, that how to enhance the propylene yield during the operation. So, that is the cracking by Jettison 5. So, operating conditions, temperature, pressure, everything is very important, right, residence time. So, in order to avoid the coke formation, and that is what I told, a FCC or fluid catalytic cracking is very important in this case. So, cracking, if you have a zeolite materials, right, you get a different kind of combinations here, and if you do not control that, then secondary reactions also take place, and that will give you naphthenes, paraffins, aromatics, right. That is what I told you, gasoline range of hydrocarbon, right. So, oligomerization, that is the olefin forms and they oligomerize, and you will have the larger molecular weight compounds, and that is what the polymer gasoline, right, during the reforming reaction. So, different combinations, and one needs to control for maximization of propylene, the secondary reactions are to be suppressed, and a new catalyst or a novel catalyst system is to be designed. So, I stop here, right, and so thank you for your attention.